Welcome. In this video I'll introduce coordinate systems, and these are often used in particle physics to represent and make our problems easier. By transforming into a different coordinate system, some of the problems move into the coordinate system itself, becomes more complicated, but the problem can be written in a simpler way, and this often makes the solution easier and numerical solution more accurate. So I'll introduce coordinate systems by first introducing a quite common one that's used in tokamak physics, and this is cylindrical coordinates, and then use this as an example to introduce some basis vectors and ways that vectors can be transformed and derivatives can be transformed. And so this will be then used in later videos to understand more complicated flux coordinates and non-orthogonal coordinate systems. So if we start with the Cartesian coordinates, we have a z example here, we have an x coordinate and a y coordinate. So in this basis, which is the one I'm probably most familiar with, we have three coordinate axes which are all orthogonal to each other. So these are all right angles between all of these. Just write things like position vectors. So if you have if this is the origin here, you have some kind of vector to a position, and this is the vector p. We can just write this p as a combination of px in the x direction plus py in the y direction plus a pz in the z direction. So we just have three components, x, y, and z, because it's a three-dimensional system. We're just used to writing this as a unit vector in each direction. In more complicated coordinate systems, there are two different ways of writing the same vector. So p can be written as components of two different kinds of vectors, and we'll see that we have to be a bit more careful about how these vectors are defined and how we use them. So in a Cartesian coordinate system like this, the x components and the x vectors are essentially defined by how does the position vector change as you change x, for example. So x in this case is defined as essentially the change of the position with the coordinate x, and the same y is the change in position with coordinate y. Now when we have to consider two different kinds of basis vectors, this will actually be called ex, and this will be ey, and it's with a y lower. So we have a ez, look like this, is dp by dz. So these are the basis vectors that we're used to in Cartesian coordinates, and these are the tangent vectors. So as if you have a vector p, how does that position change as you change one of the coordinate axes? And so these lines are tangent to the coordinate lines. So lines of varying x and keeping y and z constant, for example. So if we try a slightly more complicated coordinate system, so cylindrical, so now we have we still keep the z direction, and now I can draw on the x and y just for so you can see them still. Now we're going to transform into a different coordinate system where you have a radial coordinate. So this is a polar coordinates in r and in x and y, and we have an angle phi, and this angle is going around. So we have an angle coordinate which goes around in x and y, and we have a z coordinate which moves up and down. And so we can write that we have, for example, x is r cos phi, y is r sine phi, and z is just equal to z. And then we can, of course, invert this, so we can work out what r and phi are from x and y. So we can just say that r is just square root x squared plus y squared, and tan phi is just y over x. And these are useful for transforming between Cartesian and cylindrical coordinates. So now in this case we want to work out again how do we write a vector. If we have a position, so we have some vector here, position p. How do we write this vector? So we have three components still, because it's still three-dimensional. We want to write p's in terms of different tangent vectors. So the tangent vectors here So we'd like to write that we have, so P is, as before, so we have some X component, which is basically an R cos phi times, that's in the X direction, plus the Y component, which is just R sine phi in the Y, plus Z. So Z in the Z direction. So these are all the unit vectors x, y, and z in Cartesian coordinates, and then the position P as a function of r, phi, and z is given by this. And so we can work out the tangent vectors. So we write down the tangent basis vectors by differentiating the position P with respect to each of the coordinates. So the tangent vector in r is just cos phi in x plus sine phi in y. And we have similarly, we can work out the tangent vector in phi. And these are functions of phi and r. So for example, if you're at this location over here, the tangent vector in r is this way, so ER is out here, and E phi is out this way. So this is, if I follow along phi, I'll just move along this line here. Whereas if you're over here, for example, ER is out that way, and E phi is this way. So ER and E phi are now functions of position, and so they're no longer constant. So when you differentiate them, you have to be a bit careful because they change in space. There's another thing which is slightly different about them compared to the Cartesian coordinates. If you look at the magnitudes of these vectors, so ER, for example, dot product with ER, that's just cos squared plus sine squared. This is just 1, as you'd expect for a Cartesian. And then if you look at E phi, for example, dot with E phi, this has a slight difference. Here you get sine squared with an r squared, and here cos squared with an r squared, so this just becomes r squared. And so the phi basis vector, the tangent vector, has dimensions, so it's dimensions of length, and it has a non-unit size. And so you have to be a bit careful when you write down components of vectors that in general, the components of the vector can have a different unit from the vectors themselves, because the basis vectors can have units. And these factors here, these are called scale factors. So this is h phi squared, which has units and magnitude as well. But using these vectors, we can write down a position or any vector really as the sum of different components. So what we do is, in order to denote which kind of components we're talking about, we have to keep track of these indices. So for the basis vectors, the index is down. That means for these components, the index is up. So PR with R up times ER plus P phi times E phi, PZ times EZ. Okay, so I have 3 components, PR, P phi, and PZ, which you can represent a vector using these basis vectors. So you can write things in terms of R, phi, and Z coordinates. The other thing we might want to do with quantities in different coordinate system is differentiate. So I want to take derivatives, and this will lead on to the idea of reciprocal basis vectors. So in Cartesian coordinates, used to writing the derivative operator del as just a combination of different components. So you have x, so you have d by dx, d by dy, and d by dz. So you can take the gradient of a scalar, for example, or dot product with a vector, and everything behaves quite simply because these are all orthogonal and they all have unit size, and so you can each component works kind of independently. In general, this is written slightly differently. So we actually use the chain rule to say that the gradient is the gradient of each coordinate. So gradient of x example, d by dx plus grad y d by dy plus grad z dy z. So in Cartesian coordinates, these are the same things. So the grad x and grad y, these are all just unit vectors in each direction. But the same expression works in more complicated geometries. So in cylindrical, so we have the gradient operator is, and now we have three vectors here which are new. So there's grad r, grad phi, and grad z, and these are another set of independent vectors that can be used to describe vectors or gradients, and these are the reciprocal bases. And so we have two kinds of bases, or two sets of vectors that we can use to describe directions in coordinates. So we have the E r, E phi, E z, and we have the grad r, grad phi, grad z. So we have, in summary, there's E r, E z, and is the tangent, and then there's these grad r, grad phi, grad z, and these are sometimes written as E r, E phi, and E z. So these are the reciprocal basis vectors, and it's equally valid to write vectors in either of these forms. So any combination of these three or any combination of these three, they're just equivalent ways of writing vectors. And they have a very useful property, which is that the dot product of these two is the Kronecker delta. So for example, EI, by which I mean where I can be r, phi, or z. Dot product with any of these, so E, J. So again, J can be either r, phi, or z. Is delta I, J, which means that ER, for example, is orthogonal to both E phi and EZ. So e.g., so ER is perpendicular to E phi and EZ. As long as we're careful about whether these indices are down or up. So that's the one thing to be careful about with these coordinate systems. Okay, this is very useful because then you can calculate what the components of vectors are by taking dot products with these vectors. So for example, if you want to know what is the component PR, well, if you want to take the dot product of this with E lower r, you might end up with 1 here, but in general these components can be non-zero as well. So ER may not be orthogonal to these, whereas the gradient of r is orthogonal to both of these two. And so you can write that, for example, if you grad r dotted with a position vector, all the components disappear except the first component. So you just end up with PR, then grad r dot this, and then these are 0. So this is just PR grad r dot E r, and then this is 1. So this is just equal to PR. And so this gives a way of working out what the components of these vectors are. So lastly, just work out what are these components. So what is so the easiest way of finding out what these are is just by writing down what they are in terms of Cartesian coordinates. So you just say that r is just square root of x squared plus y squared. Phi is just the inverse tan of y over x. And then you can differentiate and just take the gradient of r in Cartesian coordinates. So we write it out in Cartesian coordinates. Obviously r doesn't depend on z, so that goes to 0. So after a little bit of manipulating, you can quickly work out that this dr by dx is just cos phi, and dr by dy is sine phi. So that gives you the expression for grad r. And the same way you can write down what grad phi. And note in this case that grad phi has a 1 over r, whereas E phi had r. And so, for example, you can do grad r dot grad r is just equal to 1 in this bit, but grad phi dot grad phi is, well, this just becomes sine squared plus cos squared again, but we have now we have 1 over r squared. And in this case, this is the same as 1 over h phi squared. So it's the inverse of e phi, but this is because it's orthogonal. Because r, phi, and z are all orthogonal, then this reciprocal relationship works. So the magnitude of grad phi is 1 over the magnitude of e phi. In general, that's not true if you have a non-orthogonal system. Okay, so in summary, this is some of the mechanics for dealing with different coordinate systems. Things get a little bit more complicated in non-orthogonal coordinate systems, but not much more complicated. So this is most of it. So yeah, in summary, we have 2 basis sets. So we have 2 sets of vectors, e r, e phi, z, and the reciprocal of those, so it's grad r, grad phi, grad z. They have a nice property that they are orthogonal. These 2 sets are orthogonal, and so you have that this. So you have the e I dotted with e j. If one is down, one is up, you get delta I j. So it's 1 if I equals j, and 0 otherwise. And this means we can write all vectors. So if you have some vector u, we can write it as basically the sum over the index I of the u components. So u I e I, for example. Or you can write it as equivalently sum of I of u lower I e I. And so you have the component, and you have the basis vector, and we can use this property that they're orthogonal to calculate these components. So u I is u dotted with e I, and the same. So some of the terms used gets a bit confusing because people call these things like contravariant or covariant components, or contravariant covariant vectors. The point of these are that this is the same vector. You can just write it in 2 different ways, and so these components vary in different ways as you change coordinate system. So this is the contravariant component, and this is the covariant component. Okay, next lecture I'll try and expand these and explain how it applies to non-orthogonal coordinate systems, so flux coordinates for magnetic field alignment. Okay, thank you.